Okay, so I'll be going over the 2024 past paper for physics, and I'll try and go over paper one and paper two today. So only paper one in this video, but then I'll upload both videos overnight. So hopefully the day before Monday, so on Sunday, um, it's accessible. Now I do recommend accessing other resources instead of watching my videos because I mean, like, seriously, like, I'm not the best resource. No way. Okay. Which option? Okay, question one. Which option describes a feature of baryons? Baryons are a type of hadron. So hadrons are quark composites, right? So baryons are actually comprised of three quarks. They have three quarks, or they could have three anti-quarks. So it's going to be B. They're not a type of elementary particle, they are a composite, right? Electric charge doesn't equate to that. No, not always. Actually, you can't even get that with the combination, with any combination of quarks, of three quarks. Yeah, I don't know why I'm switching the screen. Okay, so it's going to be B. Which property of light is described by the postulates of special relativity? Okay. Wait, did I say postulates or property? Okay. Regardless, let's look at the choices. Okay. Postulates of special relativity. Okay, we know that the speed of light is constant in all inertial frames of reference, and that is C. Okay, so it's going to be C. Yeah. The other postulate is that the laws of physics are the same in all inertial frames of reference. I think that is. I haven't revised too much for physics. So, yeah. Two objects with masses 65 and 75 kilos, respectively, are separated by 1.5 meters. What is the gravitational force of attraction between them? Okay, this is a part where we can use this. I've changed the application I'm using um, to record, so it might be better, hopefully. Yeah. Okay, so we have force of attraction due to gravity. So Fg equals big G m r squared, right? We know that big G represents the gravitational constant, 6.67 times 10 to the negative 11. We know that the masses are 65 and 75 kilos. No unit conversions necessary. And then 1.5 meters squared. We just put that in a calculator. Okay, we get an answer of 1.45 times 10 to the negative 7. So it's going to be D. And it is. Two experiments were conducted, and the following observations were made. Experiment 1, light passing through a double slit. So this is describing Young's double slit experiment. Produces a diffraction pattern. So that supports the wave model of light. Haven't I done these questions before? Of a specific frequency, the light incident on a metallic surface produces photoelectrons. Maybe I haven't, or it just seems very similar, with discrete amounts of energy. Which statement can be supported by the observations? A wave theory of light can completely describe. It won't completely describe because experiment 2 supports the particle model of light. Okay. Bending of light is a result of light behaving as a particle. No, it's because light is behaving as a wave. Particle model only describes some. Yes. D doesn't make sense. Light waves Only light waves can travel in a vacuum. Uh, no. That's not supported by the observations. There's nothing in the observations that support that. So, yeah, let's see. Magnitude of the electrostatic force between two positively charged particles. That is like 1 over 4 pi epsilon naught. Was that it? I forgot. Okay, so that's the force due to the electrostatic force. Okay, so the force between two positively charged particles is, let's, inversely proportional to the square of the distance. Yeah, it is. So could be A. Probably is A. Increases as the square of the distance increases? No. That contradicts what A is saying. Is proportional to the square of the distance? No. Is unrelated? Okay, so they're all talking about the square, so it's going to be A. The graph shows the relationship between masses of different objects and the gravitational force they experience on an unknown planet's surface. Determine the gravitational field strength of an object at the planet's surface. We need to take note of the units. Yeah, that's pretty important. So in this case, you have gravitational force on the side and mass in grams. So we need to divide that by 1,000. So the gradient represents force due to gravity over mass. So the gradient would be um, the would be equal to the acceleration, the gravitational field strength, or yeah. Okay, so we can get 100 minus 20 over 2 kilos minus 0.4. I think that's what it says. So it's 1.6. It's going to be 50. Okay, so that's D. An object experiencing a gravitational force of 50 newtons moves down a frictionless incline of 40 degrees to the horizontal. Okay, 40 degrees. You have a gravitational force strength of 50 newtons. Frictionless incline. There's no force due to friction. In terms of the force acting on the object, we can kind of neglect the perpendicular or the vertical force components. Let's just talk about the parallel. So it's frictionless, so there's no force of friction going up the plane. So to get this, you just get theta, which is 40 degrees. It translates over here due to complementary angles, and then we can get the net force, which is just equal to this force, this parallel force from gravity. So we're resolving it into parallel perpendicular, but we're only after the parallel force in this case. This is actually sine of 40 degrees, even though it's the parallel, because the angle is up here. So 50 sine 40 degrees. It's going to be 32. It's A. An object is pulled in two different directions as shown. What is the magnitude of the net horizontal force acting on the object? Um. Okay. There you have 30 going this way. Since we're after magnitude, what we need to do is find the horizontal and vertical and then just do Pythagoras. 60 degrees, 120. Net horizontal. Oh, okay. That makes it a bit easier. So we're just after this part. So that's cosine. So 120 cosine of 60 degrees minus 30. Cosine of 60 degrees is a half, I think. So we just halve 120. We get 60 minus 30, which is just 30. Should be D. Yeah. Passenger at the center of a train moving at relativistic speed switches on a light. According to the passenger, light travels outwards as shown. How would a stationary observer watching the train pass by them record this event? Okay, this is interesting because I think it doesn't matter. It doesn't matter that they're moving at relativistic speed because let's say I'm an observer, you're the passenger in the train, and then you turn on the light switch. Maybe it's an old-fashioned light switch. You have to pull the string. Yeah, light comes to me, and then I see what happens. Okay, so this is weird, to be honest, if you think about it. Do I just have like unbelievably fast reaction time, or I don't know. How would a stationary observer watching the train pass by them record this event? Hmm. Thing is, technically, wouldn't it reach the back first? If it's moving to the right, wouldn't it reach the back first? But I'm pretty sure since it's a stationary observer, since I'm a stationary observer, it would be identical. This is not good. Because we know, according to, this first or second postulate of special relativity, speed of light is constant. So then speed of light, the light that turns on, it will travel left and right simultaneously at an equal speed, but the train is actually moving. Well, to you guys, it's moving this way, right? So then it would reach the back, which is this hand, first, since light's. Hmm, we'll see. I think I have an explanation for both scenarios. It's not C, right? It hasn't even turned on. What are you talking about? Um, D? Ooh, okay, so it is. Okay, yeah. So I was actually right in terms of saying that. So, even though regardless you're a stationary observer, since the train's moving to the right and light's constant in your frame of reference, wait, but you're not in an initial frame of reference to the train. Hmm. But light, regardless, is going to move at the same speed, and then the train, since it's moving this way, this way, it's going to reach the back first. It does make sense. I was a bit skeptical, but yeah, it does make sense. It would be simultaneous for the person in the train, right? They're in an inertial frame of reference, it would be simultaneous. An experiment was conducted to determine the force experienced by an 85 centimeter wire with a 22.4 amp current flowing through it. In an external magnetic field, it was rotated through varying angles within the magnetic field such that... Okay, maybe I shouldn't just read the questions out loud. I don't know. Maybe perhaps someone's deaf that's watching this. Maybe, but some chance, to be honest. Like the low chance, but yeah. Anyways, it was rotated through varying angles within the magnetic field such that data analysis identified the relationship as F equals 0.0306 sine theta. What is the order of magnitude of the strength of the external magnetic field? Okay. I think this is referring to... I haven't done physics in a while. BIL sine theta. I think it's referring to that. So BIL in this case would be 0.0306. We're given current, so we divided by the current, which is 2.4. We divided by the length, which is 0.85. So we converted it to meters. So 4 times. Right, so we get an answer of 0.015, but that's not the question they're asking. They're asking for the scientific notation. So it's times 10 to the negative 2. So it's B. A planet orbiting a star has an orbital radius of 6.4 times 10 to the negative, not negative, 10 to the 14 meters. And completes a full revolution, so the period, every 1.5 Earth years. Okay. We need to convert years to seconds since we're calculating the mass. Yeah. Okay. So in this case, we're going to be using the combination of gravitational, the force due to gravity, and centripetal force. So when you combine them, you get this. It's on the formula sheet. We're trying to find the mass of the star. The mass of the star, so capital M is whatever is the mass of, it's the common central mass that the planet is orbiting around. So to rearrange, simply multiply it by r cubed on both sides, divide by t squared on both sides. So that's what happens. Okay, then we sub in the radius. It's 6.4 times 10 to the 14, and it's in meters, so we don't need to have to worry. However, for this, we do have to worry. We have to convert 1.5 to days, which is we times it by 365. We times it by 24 to get hours. How many minutes are in hours? There's 60. How many seconds are in minutes? There's 60. So then we square that entire bracket. And then you put that in our calculator. 4 pi squared times brackets 6.4 times 10 to the 14. I'm getting a little hungry, so I need to hurry up. Yep, that's my motivation. Okay. So I'm just timesing it. I'm making mistakes everywhere. Oh no, this is not good. Okay. We get an answer of 6.9 times 10 to the 40. That's reasonable for a star. So let's see. Okay. The horizontal displacement of an object experiencing projectile motion was measured and recorded against the cosine of the launch angle. The initial velocity was kept constant. What the launch angle would cause the object to land 1 meter from its starting position. Okay, well, let's see. On the graph, if you go to 1 meter, you could say it's approximately 0.12 for the x value. Okay. So to get, according to the trend line, the line of best fit, it's cosine theta. Cosine theta equals 0.12. Theta equals inverse cos of 0.12, right? Cos of 0.12. Make sure you're in degrees. Remember in the exam, or radians, depending. I mean, in physics, they usually just use degrees. So you get 83. So it's D. Light with a frequency of 9.4 times 10 to the 15 hertz is incident upon an unknown metal, producing photoelectrons and a maximum kinetic energy of 5.6 times 10 to the negative 18 joules. What is the work function? Okay. So in this case, we have EK max equals HF minus the work function, right? We're given that EK max, so the maximum kinetic energy of the photoelectrons is 5.6 times 10 to the negative 18 joules. We know that the light has a frequency of 9.4 times 10 to the 15, but we know that Planck's constant is 6.626 times 10 to the negative 34. So we multiply it by the frequency, and then what do? We add the work function on both sides. And then we subtract by the maximum kinetic energy of the photoelectrons. So we get this. It's not focusing. How do I get it to focus? So then 6.626 times 10 to the negative 34 times 9.4 times 10 to the 15 minus 5.6 times 10 to the negative 18. However, we're not done yet. We can notice that the answers are in electron volts, so we need to divide this by 1.6 times 10 to the negative 19 for the conversion. We get an answer of 3.9. So it's B. Magnetic flux density. It's B. It's the capital B. That's the symbol. Magnetic flux density is synonymous to magnetic field strength, right? So you might have heard those terms before. Hopefully you have. So is it related to the rate of change of field lines moving through a given area? No, that's more like EMF. That's more in line with Faraday's law. The induced electromotive force is directly proportional to the rate of change of magnetic flux. The number of field lines per unit area. Yeah, yeah. Density, how much in an area. It's kind of, well, density is not really related to that. It's more like weight per volume. I mean, mass per volume. Same thing. It's something per something, right? It's a big. Which direction does centripetal force act? Okay. Well, I've got a question for you. Yeah. Well, let's do a demo. Okay. I just have this. It's like a button tied to a string. If I spin this fast enough, you should be able to hopefully see it. Um, yeah. So here you have centripetal force happening. Um, well, yeah. If this button was heavy enough, right, or if it was heavier, the centripetal force required to achieve the same like velocity, the tangential velocity, it would be much greater, right? So I would feel a lot more force feedback on my hands and fingers. Also, if I decrease the radius, that should increase it. But then I can't really achieve the same speed. The same, yeah. Okay. Either way, we know that this, if I were to let go during motion, it would just propel itself in a direction that's tangential to its trajectory. I mean, tangential to its. Okay, trajectory kind of makes sense. Or it's just motion, right? So in its circular motion. But to prevent that, we need to have acceleration, right? Velocity is going this way. But to prevent that and make sure it maintains this uniform circular motion, acceleration needs to happen perpendicular. Acceleration needs to be going down towards the center of motion. In this way, it will curve, right? And it's always going to be perpendicular. That's what keeps it uniform and circular. So it's going to be towards the center of motion. So it's going to be A, right? Question 16. The table shows a combination of mediating particles and possible forces they experience. Which row is correct? Photon does not mediate the strong nuclear force. It only mediates the electromagnetic force, so it's not A. B. Leptons do not experience the strong nuclear force, so it's not B. And leptons also experience the electromagnetic force. So yeah, that's another reason why it's not B. Quarks, they experience the weak nuclear force. I'm pretty sure. Pretty sure they do. Do they not? So it can't be C, so it's D, right? Yeah. Mesons are basically just quark composites again, but rather than like for example, baryons. Baryons have three quarks or three antiquarks. Mesons are a pair of a quark and an antiquark. So it would basically be synonymous with C, but C in this case is incorrect because quarks do experience the weak nuclear force. Person on Earth experiences a time dilation of 15 years. Approximately how much time will pass for a passenger on a spaceship traveling at 0.7 or 70% the speed of light relative to Earth during that time? Okay. So they would have experienced a shorter amount. So it's going to be A or B. Okay. Let's actually calculate it. So in this case, dilated time would be the person on Earth. I was actually planning on using my whiteboard today, but I don't think it's actually uh, more suitable. So all we're doing is subbing in the values. So V is 0.7C. C's cancel, leaving us with 15 square root. So I multiply by the square root on both sides. 0.7 squared is just 0.49. And then you get 15 square root 0.51. 15 like multiplied by the square root. So you get 10.7, which is around 11, so it would be B. Electromagnetic waves are produced by an oscillating electric charge, resulting in an interaction between magnetic and electric fields. How are these two fields aligned? They are perpendicular to each other, but none of them seem to have any relations specifying they're perpendicular. They're not parallel, so it's not A. They're not varied in their wavelengths, they're in phase. It's not B. Synchronized in oscillations. Yeah, they are synchronized. They're in phase, yeah. Wavelengths would be the same, so it contradicts B. D is not correct. They intersect at the nodes. Is that correct terminology? So when they have like the middle of the middle between the crest and the troughs. Yeah, so it would be C. A 7 microcoulomb charge requires 1.5 times 10 to the negative 8. Is that microcoulomb? I think it is. 1.5 times 10 to the negative 8 joules of energy to be moved between 2 points in an electric field. What is the order of magnitude of the potential difference between the 2 points? Okay, let's write those down. Okay, so in this case, this amount of energy is used to move the charge. Yeah, that's basically it. Voltage, I think on the formula sheet, can be represented as the change in internal energy over charge. So I think that's what we use. So in this case, it's just 1.5 times 10 to the negative 8 divided by 7 times 10 to the negative 6. I believe that's the correct answer. So in this case, what you'd have is B, because that's the order of magnitude. Identify the defining feature of a black body. Okay. All frequencies of electromagnetic radiation are absorbed or emitted. Yeah, that is actually the characteristic. So according to quantum theory, that does occur. So it's probably A. Light with 2 wavelength peaks is emitted at a specific temperature. It's not 2 wavelength peaks. I'm pretty sure there's only 1 peak on the blackbody radiation graph. Electrons are emitted in the presence of all frequencies of light. Electrons? I don't think electrons are emitted. It's photons. The peak of its spectral output does not vary with temperature. It varies with temperature. If you look at the formula sheet, you notice that the maximum wavelength is inversely proportional to the temperature of the black body. And then in the numerator, you have like Wien's displacement constant. So in the quantum theory part of the formula sheet, you have lambda max equals lowercase b over capital T. Lowercase b represents Wien's constant, and this is given in the formula sheet so as 2.898 times 10 to the negative 3 meters Coulomb, not coulombs, meters Kelvin. Yep. So there it is. So it's going to be A. Describe the particle interaction shown. An electron and a positron annihilate, forming a photon, and then the photon decays back into an electron and a positron. But it creates a new electron and a positron that have a different amount of energy. Interaction between electron and positron. During this interaction, the two particles are annihilated. Yup. They then pair produce. Are we meant to specify pair produce? Hopefully not. I mean, I created that. I said that they create another, like, different electron and positron. I'll give myself a 4. I didn't say pair produced. I don't know if you're meant to. I mean, it says you're meant to, but maybe they'll accept that answer. Special relativity accounts for the observation that more muons from cosmic rays are detected near Earth's surface than expected. Explain this phenomenon by outlining why Newtonian physics cannot explain the scenario, while special relativity can. So refer to the frames of reference of both the traveling muons and the observer near the Earth's surface. Okay. So, according to Newtonian physics, muons have too brief of a lifetime to reach Earth's surface because muons have a very short lifespan, like 2.2 microseconds or nanoseconds, something like that. And because of that, however, special relativity, or no, I should say what observations occur, right? However, more muons reach the Earth's surface than Newtonian physics predicts. And then that's because special relativity, time is relative as suggested by special relativity, since the relativistic speeds allow the muons to experience time dilation and length contraction. So due to the combination of these events, it extends in the observer of the according to the frame of reference that of the observer at or near Earth's surface, the muons would be traveling longer than expected due to the time dilation, and also due to length contraction, the traveling muons in the frame of reference of the traveling muons, they only need to travel a shorter distance than the length measured or observed by the person on or near Earth's surface. That was a very convoluted kind of response, terrible response. Do not, oh my days. Do not rise. Oh, wow, okay. Since muons are short-lived, so short half-life, I said something to that extent. I don't know what words I said, but they shouldn't reach. Okay, I got 2 marks for that. And then identifies that muons travel at relative. Yeah, I did say relativistic. Yeah. Explains that observer's frame of reference, muon's half-life will be longer. Okay, I did say that. Explains that muon's frame of reference, length contraction. Sample response very short and brief. But yeah, I think I got 5 marks for that. An experiment was conducted to study an object undergoing circular motion with the radius of motion acting as an independent variable and speed kept constant. The data comparing the period and radius of motion is shown. Okay. We're dealing with circular motion, so immediately we should be thinking of our formula sheets. Fc equals mv squared over r. Right? So if we have a graph. Oh, okay. No, don't use this formula. Use the other formula. So v equals 2 pi r over t. Right? This is just a simple displacement over time formula to get speed. That's the distance. That's the circumference of a circle. And then time for one revolution is just the period. Okay. So identify the period expected for a 25 centimeter radius of motion. So we can just use our graph. 25 centimeter radius. It's going to be around here. So approximately what? 0.21. Yeah, something like that. So 0.21 seconds. Okay. Determine the constant speed. So is it 0.21? 0.21, yeah. Determine the constant speed. We're going to be using the gradient. The gradient in this case represents period over radius. Well, what does the gradient actually represent? Okay, we can use the value of 0.5, 0.4, so in terms of x and y. And then we can just probably assume, maybe not, maybe. I mean, we can assume that, oh, I'm a bit tired. Okay. We can assume that 0, 0 is a point. I feel like we can assume that, but we won't. We'll use 0.1, 0.1. Okay. So I've subbed in those values, so y over the change in y over the change in x, just rise over 1. That's very simple math. So we chose 0.4 and 0.5 as our final point, and then we got 0.1 and 0.1 as the initial. So 0.3, 0.4, which is just 3 over 4. All right, if you simplify it. Okay. But what does the gradient actually represent? If we rearrange this formula, we multiply t on this side, we multiply t, and then we divide by r, we get this, and then we divide by v. This represents v, by the way. This is the gradient, so 3 over 4. Actually, no, I should have just done 1 over, so inverse of the gradient. So 2 pi times 4 over 3. So So that's 8 pi over 3. That's the velocity. Eight point 3.8. Eight 8.38. Full marks for that. Okay, the atomic energy level diagram for an unknown multi-electron ion is shown. Calculate the wavelength of light emitted as electrons move from 4 to 2. So it emitted because it went down the energy state, so that's why it lost energy, right? So 4 to 2, well, let's see. So, what do you have? Um, if we go from n to 4 to n to 2, what's the change in energy? So it goes from 3.4 electron volts, then we minus negative 13.6. So what do we get? We just get 10.2 electron volts, right? And we can double check that, you know, negative, negative makes it positive. There's that. And then minus 3.4, 10.2, yeah. Okay, so that's the energy. We're trying to find the wavelength. Okay. So that's the energy emitted. That's the energy that the electron lost, and therefore it emitted all that energy as a photon with a specific wavelength, right? So we need to first convert this to joules. So 10.2 times 1.6 times 10 to the negative 19 joules, right? That's the energy. To get the wavelength of the photon, we use E equals HF. That's the formula. Using the wave equation, so V equals F lambda, we can rearrange for F. In this case, we're talking about light, so it's actually C as V. The speed of light is the velocity in this case. We divide by lambda on both sides to rearrange for F. So this becomes HC over lambda. So therefore, lambda equals 6.626 times 10 to the negative 34 times 3 times 10 to the 8 all over. So we rearranged E and lambda. So E is 10.2 times 1.6 times 10 to the negative 19. We just put that in a calculator, and then we should have an answer. Okay, so we get 1.22 times 10 to the negative 7 meters. The question actually specifies in meters, not nanometers, which is a bit unusual. Okay, let's see if we're right. So 1.22, yeah. Okay. A photon with 40.8 electron volts of energy is incident on the unknown ion and collides with an electron in the first energy level, so n equals 1. Explain what would happen within the ion in terms of the photon and electron. So the photon would be completely absorbed by the electron at the first energy level. And because of that, it would excite the electron enough to make it, to allow it to transition to the next energy level, which is n equals 2, right? It has sufficient energy and the specific amount of energy. So here we have n equals 1 being at negative 54.4 electron volts. We add 40.8 electron volts. What happens? Well, guess what? We can put that in a calculator. I mean, we shouldn't need to, but just, yeah. We can see that the addition of energy equals the amount of energy in the second stationary state or energy level, right? We get negative 13.6 electron volts. So the electron that absorbed the photon, that completely absorbed the photon, now has enough energy to actually transition into the second energy level and becomes excited, right? So now it's at n equals 2. After a given time frame, the electron would eventually lose the energy, so it would emit a photon with the same amount of with the same wavelength, same frequency, same amount of energy as what it initially absorbed, and then it would transition back down to the first energy state. The photon will be absorbed. Since the photon energy of 40.8 electron volts corresponds to the difference in energies between the first and second energy levels, an electron in the first energy level will absorb the photon and jump to the second energy level in its excited state. Okay, but you could say that eventually it would it would emit back out. Explain how a transformer with a turns ratio of 48:1 is set up to reduce a 240 volt input. Explain how a transformer works in terms of Faraday's law and electromagnetic induction. 3 marks. It's probably a short response. I mean, it is a short response, but like, it's probably not too much writing. First, you need to recognize that transformers only work in alternating current, so AC. You need AC to work. You need to use AC because of Faraday's law. What is Faraday's law? You need to use alternating current as it allows there to be a change in magnetic flux, which corresponds to Faraday's law, as a change in magnetic flux will induce a electromotive force, or it will create a potential difference that is directly proportional to the rate of change of magnetic flux. And then electromagnetic, how do you relate it to electromagnetic induction? I haven't revised too much on the definitions. It's just like, from the primary coil, when there's a change in magnetic flux, that will induce a current in the secondary coil, allowing the voltage and the current to be altered. It's something like that. Something. I don't know. When a magnetic flux is linking a circuit, when the magnetic flux linking a circuit changes, an EMF is induced in the circuit proportional to the rate of change of magnetic flux linkage. So I did describe that. Therefore, in a transformer, the changing voltage in the primary coil will affect the rate of change of magnetic flux in the secondary coil. Current will be induced in the secondary circuit. Changing voltage in the primary coil will affect the rate of change in the secondary coil. I didn't really say that. I wouldn't say I said that. I did say the current is induced in the secondary coil, but I wouldn't accept my answer. Yeah. Whoa, 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 whoa. Okay. I'll be honest, I think I saw the answer. It was like 5. But regardless, it's a 1 mark question. Doesn't really matter too much. So it does matter. But okay, so we can use this formula. The voltage of the primary coil over the voltage of the secondary coil. And then this equals the number of turns of the primary coil divided by the number of turns of the secondary coil. So the output voltage would be just the voltage of the secondary coil. So we can use this formula, right? Okay, and we're given that we have a 240 volt input, so that's the primary. 240 over voltage of the secondary. So we're trying to find the output voltage, which is the secondary coil voltage. Number of turns, it's 48 over 1, so that's the ratio. And in this case, since it's a fraction, so we can just use this. So then we do the inverse, so we just flip both sides. So Vs over 240 equals 1 over 48. And then we just multiply by 240 on both sides. So it's 240 divided by 48, which is 5, right? And that was the answer. Yeah. The centers of two small equally positively charged metallic spheres are separated by a distance of 0.3 meters and experience a force of 0.025 newtons between them. Calculate the charge on each of the metallic spheres. Okay, I wasn't very space efficient in terms of like my book work. Yeah, that's not good. Okay, let's look at the question again. I should move myself out of the way. Okay. Centers of two. So we're dealing with electrostatic force. So we're going to be using this formula, right? We're given the force, it's 0.025. This, I'm pretty sure, equals 9 times 10 to the 9. It's on the formula sheet. They're equally positively charged. So it's Q squared. They have the same charge, you're multiplying by the same value, so you're going to square them. Okay, and then you have radius, which in this case is 0.3 squared. Okay, rearrange. What do? Multiplying both sides by 0.3 squared, which is just 0.09. You divide it by 9 times 10 to the 9. And then you square root everything to just get Q, since Q is squared. So let's say you don't know where the value for 1 over pi epsilon, 4 pi epsilon naught is. You can go to the electromagnetism part in the formula sheet and find Coulomb's constant, so 9 times 10 to the 9. Yeah, okay. So what we do, we just plug this into the formula sheet. Or not the formula sheet, the calculator. I swear these days I keep saying random things, you know, like genuinely. Like I'm trying to say something and then I just say something like that's completely unrelated. Okay, it's going to be 5 times 10 to the negative 7. Yeah. Here's the marking guide. Just, you know, you can pause if you want to. On another planet, an object was projected. So this is the last question. was projected upwards from an initial height and took 0.71 seconds to land. The relationship between vertical displacement and time is s of y equals, so it's a quadratic factor or quadratic function. So we're given a time for it to land. We're given vertical displacement and time, so we can sub in the time to find the vertical displacement. Pretty simple, pretty straightforward. Okay, so time equals 0.71 seconds. Then so s of y, all we need to do really is just, we can actually just graph it, if we really want to do that. I think I've typed it in correctly. So negative 5.18x squared plus 3.5x, which in this case, x represents t, so time. So obviously, at 0.6, okay. 0.67567, oh my days. Okay, no, they've got to be trolling. Okay. Anyways, so the root of this function, right? We're ignoring the root at 0 because, well, that's just at the start. That's the initial position. So the reason why it's not this is because, well, guess what? It's elevated. If this was not elevated, this would therefore be the time it takes to touch the ground. But it is elevated, so it's not. We just sub in 0.71, we find the value. Okay, so we get an answer for s of y, negative 0.126238. It's actually not an irrational number or just some number that, I mean, it wouldn't be an irrational number anyway. Yeah, since you're not dealing with square roots. Okay. Sum the horizontal displacement of the object when it lands. Okay. From this, we're given s of y. We can work backwards. So we know that s of y equals u of yt plus half gt squared. S of y is this value. We're not going to sub in yet. U of y equals u sine theta, and in this case theta is 30 degrees. T plus half gt squared. Half of g is negative 4.9. We have this. Then what we can do is we can use the point we've found. So at t equals 0.71, we know that sy equals this. So we can use that to work out what u is. I mean, technically, you could probably just calculate it by equating this with the relationship given in the question. So the coefficient of t was 3.5, so this equals 3.5. Since sine of 30 degrees is a half, then u equals 7. Let's see if that checks out. Okay. So we know equals, so s of y, okay. S of y plus 4.9t squared, and then we divide it by, well, this is a half, right? So you're going to times it by 2. You're dividing it by t, and that's u. Okay, let's see if that equals our answer. What we got 0.26238 plus 4.9, and then t squared, which is 0.171 squared. And then we're dividing this entire thing by 0.71. No, it isn't. What? Definitely put something in wrong. I don't seem to have put anything wrong, but the answer isn't correct. So that's a bit confusing, to be honest. Did I sub it in incorrectly? No, I think it's correct. Well, S of y equals. Oh, wait, no. Okay. Wait, oh. On another planet. Come on. Okay. Since it's on another planet, you can't use this. You can't use this. This is wrong. It's erroneous. No. If it's on another planet, well, the likely chances are acceleration is not going to be 9.8. Yeah. We can't use this. That's why it's wrong. So that's why we need to equate coefficients. So u sine theta equals 3.5. So u equals 7. Ta-da! Yay. Okay. So then we have the vertical displacement. So all we do is go s of x equals u of x t. In this case, acceleration is 0. S of x, we're trying to find the s of x. So u of x is 7 cosine 30 degrees multiplied by the time. Okay. 7 cosine 30 degrees multiplied by the time. This is also equal to 7 times square root of 3 over 2 multiplied by the time. Since we know that cosine 30 degrees is square root 3 over 2, it's an exact value. So then we get an answer of 4.3 meters per second. No, not meters per second, meters. Yeah. Okay. I mean, there we have it, folks. There we have it, everybody. Whoa, 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 whoa. Oh my days. 1 hour only? Okay. Hopefully it's like that in the exam. Yeah. Okay. There's paper 1 done. I'll be, after a short break, I'm probably going to upload paper 2. But for you guys, they're going to upload it at essentially the same time because it will be done overnight. Yeah. All right. See you in a bit.